Good day. I'm here again. We will be talking about our key skills for framework for quantum, and also we're going to be looking quantum entanglement states. So this period, I want us to pay attention and see how entanglement is being used. And a basic thing I want us first of all look at what is quantum entanglement. And if you see the short form and the simplest method to explain this is entanglement is when multiple objects, such as a pair of electrons or protons, share a single quantum state. And furthermore, we can see they occur when two or more particles, such as protons or electrons, are so strongly correlated that their quantum state cannot be described independently, even when they are separated by a large distance. So this is one of the definition which Einstein make use to explain what an entanglement is. It's just a process whereby we have proton and electrons using one single quantum state. So like we are having two things on one single board. Looking forward to quantum entanglement has many applications in quantum science and technology, such as we are going to be seeing it or using it in quantum cryptography, quantum teleportation, and so on, and quantum computation. So it's a basic or is most important aspect that we must understand. Likewise, we are saying that quantum entanglement is not easy to create or maintain. It's not easy to do to create or maintain. So we have to learn this and understand how it's being generated or how we can use it in on a single quantum state. If you look more, and you can still read more further online with quantum entanglement to have more understanding. And we are looking at the product state where we have the positive zero in ket. Is an example of kind of multi-qubit state known as product state. So this positive zero is an example of product state of a qubit. And we look more further whereby we are having A is equal to A0 in a matrix form of a vector A0 and A1. Likewise, we have B, products of them together, combining them together in just a normal matrices that we used to do, where we have B0, A0, B0, A1, we have B1, A0. So this extends to the rules of quantum mechanism. We switch out our probability with amplitude. So amplitude was used. So the amplitude of the state 00 is the amplitude of a qubit A, and in B, we multiply the amplitude together, where we have the amplitude of B, which is in 0, and amplitude of A. We join them together and look at how it's being processed. Let's check this work out. Suppose both qubits are measured. What is the probability that the qubit on the right, let me come again. What is the probability that the qubit on the right comes out 0 when we measure them? What's the probability? It's a question that we must be able to answer. What's the probability? This will be the sum of the probability of the two outcomes which have a 0 or the right one, namely 0, 0 and 1, 0. That will be the probability of the outcome that we may have. Also, now we are looking at the entanglement states, whereby we have the phi plus. So this phi plus is the area of having single qubit states, where phi is equal to 1 divided by root 2 of 1001. And after that, we break it down to be in an entanglement form, which is this. And also, there are no pairs of single qubit states A and B, which are in ket, whose product state will look like this. Try it for yourself, or try it whereby you are going to do some calculation and add them together so that you can see how A and B will be in an entanglement. So this represents a different kind of qubit state, and we cannot describe as combination of simple single qubit states. These are known as entanglement states. With this phi and this question is showing us how the entangled state is. Entangled gate. So before we can have an entanglement, we must have an entangling gate in quantum computing. Quantum computing typically state in a product state, specifically the state in the simplest product state of all. So in entanglement, there will be a product state. There must be a product state that combine two qubits, one qubit and the other qubit together. And with the way we are talking about the electron and the proton, both of them come together on a single qubit. Likewise, this also is going to be on a single qubit with product states, which we have to multiply them together, where all the qubits are in 0 state. If we then apply only single qubit gate, we will manipulate this individual single qubit state. So some might be rotated to positive by Adamant gate, or a complex superposition by general rotation. And also, to create an entanglement, we need to apply multiple multi-qubit gates. Please note that if you want to create an entanglement, you need to apply. That's why you need to apply a multi-qubit stage, and we are going to see the process of this, whereby the control gate of CX and CZ gate are being used as the simplest example that we can use of how we can generate it out. Okay, now if you are looking at this code, you can see we are talking of the CS gate. Now for it to be in action, I've called from Qiskit I've import, and I call out my quantum socket from Qiskit dot quantum info underscore info, import the state vector. At this point, you are going to be seeing the state vector. Here I have called upon my socket, and my qubit is in 2 qubits. So from there, if I run, I call my ket, which is equal to state vector, and I call my QC, which is my quantum socket. Also, I draw it out. If you look at the output, which is going to pop up in some minutes, now is in state vector. The output is in a state vector where we are having 1 dot plus 0 j, which is a real number or a complex one, and the dimension is in 2 by 2 dimension. That means we are having 2 qubits. But now I want us to notice something. To show it in this format, I want it to be in ket format. So I have to put it there as latex and run it again. So this is the output. Now it's giving me 0 0. So I'm having 2 possibilities or 2 qubits, which is 0 0. So moving forward, if you can see this place, this side, these are the what will I call it? These are what you can use to call your code. You can use them to add to it to have different style. Okay, now let me call. If I want it to be in sphere, you're going to have something like this. Okay, you can see now. You see, telling us that is in 0 0 and is on, and we have the face here too, and it's giving us. So this, I just write it out so that we can have the more knowledge of how to use all these keywords in our quantum or in our code. So I'm back to what I'm mainly here for. So now moving forward, now we have the CX act on 2 qubits, which are known as the control and the target. So we have the control and the target on our socket. So let's first try using qubit 0. Now we are using the 0 on the socket, which is 0 and is the control, and 1 is the target. And from there also, let me put let's run. It's still giving us 0 0. I'm moving forward. So this C0 has no effect. The state remain the same. So it's still the same when we are still using our control as 0 and our target as 1. So now we want to reverse it. So our control will be 1, and let's see what's going to give to us. For us to have is in superposition. Still the same thing. Again, no effect. This is showing us a performance that C0 is actually to be expected not to have any effect on that. So now let's look further, whereby we are using the S gate to do what? To flip the control gate from 1 to 0. So let's see, when we add a C0 gate, what is going to give to us? The C0 gate. What's C0 gate do? So now we can see it has changed. Now we can perform a CX because we've already flipped our qubit. The normal stage of a qubit or of a socket is 0. So now we have to flip it from 0 to 1, and also now make use of our one. That one should be making to be active, that it has a qubit, just like you on it. So for us to have our C0 now, let us see our CX. Let's see what it's going to give to us. Okay, sorry, it's giving me an inverter position. So let me use, it has changed and it's giving us the proper output. Now, if we apply C0, CX, it will act in a parallel on the 2 states. Okay, let's still see what's going to be here. So now, we've now flipped again, and it has changed towards 1 1. So this is our output. It has changed. It will leave the state unchanged since the control qubit there is in state, but as the control in the state as well. So the target is flipped to 1 from 0. It's going to flip it automatically. And moving to the Z gate. The Z gate whose effect is rather similar to the C0. It also acts on 2 2 qubits. Acts on 2 qubits as well, which is also the target and the control. So it also does nothing when the control qubit is in the state, but from the control state it performs a Z gate to the target. So yeah, now we can see this CX gate is also known as the control X or the control naught, due to the effect of flipping that target bit byte based on the state of the control. However, just as we saw with the C naught gate, other ways of possibility as we change it, also we can see this as well. So let's start with the case where both qubits are in positive. So additionally, we are using our Entanglement gate here. Let's see what's going to give to us. Okay, now our Entanglement gate. So from 1 point, from 0 0, we move to 0 1. From that, we start flipping them one after the other. From here, which is the normal stage of 0 of the target and the control, and from there it moves to the next one where it flip the target, and also it flip the target to 0 and move the control to 1, and also at the end it moves both control and the target to 1 as well, 1 1 as well. So moving forward now, here we will also find that the CX has no effect no matter which way that they are trying to. Here we are going to see how it's not going to have any effect. You see the same thing, not having any effect. So here we are now adding our Z gate, but these are the normal gate, which the Entanglement, which is changes, but is the normal state, positive state qubit. But now where we are adding our Z gate to it. So let's see what's going to happen. The other time we add our Z gate and he flip it 0 1 0 1. Still the same thing. Okay, let's now see what it's going to give to us. If we do the C naught X now, we will see an effect. Okay, let's see the C. Now we've done the flipping. Let's see the CX now. Let's see what it's going to give us. 0 0 1. So it's still the same. So this effect is sometimes known as phase back. So it's phase kickback when there is a superposition on both the control and the target. So that's why there is a superposition on both the control and the target. That's what I was saying the other time. There is no changes, but it's flipping it at basic, at the automatic, at the level. Also, this effect can also motivate us to make an alternative interpretation of CX. So we can think of it as applying a Z gate to control if the target is in the state of negative in ket, and do nothing if it is in the positive state of it. Okay, and I would really appreciate if you can subscribe to my channel and drop your comments. Thank you.